Okay, so let's resume with example number 2. So 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. So step number 1, we are going to show that n is equal to 1 is true, right? So how do I do that? Everywhere I see a 1, I'm going to plug in, or everywhere I see an n, I'm going to plug in 1. So 2 times 1 minus 1 is equal to 1 squared. So 2 times 1 is 2. 2 minus 1 is 1. 1 squared is 1. Boom. 1 is equal to 1. Easy. Step number 2, we are going to now assume that it's true, that it is true for all n, right? So it'll be true for 2, 3, 4, 5, all of that stuff. So now, step number 3, prove n plus 1 is true. So I'm going to do it a little bit differently this time because notice that there's only one variable. So the way I'm going to write it is going to look like this. So I'm going to say 1 plus 3 plus 5 plus dot dot dot. And I'm going to keep it as 2n minus 1. And then I'm going to add in another one. So this will be 2 times n plus 1 minus 1, right? So I have my original one, and then I have the new one. So the reason I did that is because you would not have seen the 2n plus 1, unlike the last example where I could just easily plug it in. I know I was given n, so I was able to substitute it because I had 2 variables here. For this one, I only have really 1 to work with, okay? On this side, it's very easy. This will just be n plus 1 and then squared. So let's go ahead and focus. We know, again, all of this. All right, we're going to substitute. Right? Because what is all of this equal to? It's equal to n squared. So we're going to take that guy and we're going to substitute it in right there. So it looks like this. N squared plus, let's do a little manipulation. So 2n plus 2 minus 1. And let's keep this as n plus 1 squared. So again, I'm not touching this side anymore. So n squared plus 2n plus 1 equal to, this one's a little bit easier. I have a trinomial that I want to factor. So n plus 1 times n plus 1. Same binomial written twice. So I can just write it as squared. So the right side is equal to the left side now. Right? What do I get to say? I get to say by mathematical induction, right, the above statement is true for all natural numbers. Okay, so example number 2 is definitely a little easier than example number 1. Okay, so I have one more example I want to show you. So example number 3. All right, it's going to see this. 1 squared plus 2 squared plus 3 squared. So we get the point that it keeps going up. So it'll be n squared is equal to n times n plus 1 times, oops, it's supposed to be a 2n plus 1 all over 6. All right. So if you want to pause the video and try this one on your own, absolutely can. If not, I'm going to start right now. So step 1, right, show n is equal to 1 is true. All right. So 1 squared is equal to 1 times 1 plus 1, 2 times 1 plus 1, all over 6. So 1 is equal to, so 1 times anything is not really going to change anything here. So this will be 2. 2 times 1 is 2. 2 plus 1 gives me 3. So 2 times 3 is 6. So I already know that 1 is equal to, 1 is equal to 6. That is not correct. 1 is equal to 1, and that is correct. Step number 2. All right, we want to assume n is true, right, for all of our numbers. And then we're going to the proof. So we are going to prove that n plus 1 is true. Okay, so we're going to do exactly what we did on the last problem. So notice that there's only one n value here. So I'm going to say 1 squared plus 2 squared plus 3 squared plus ... plus n squared plus, and instead of writing n, I'm going to write n plus 1 squared. Over here, I got a lot more places I have to write it. So n plus 1 times n plus 1 plus 1, right, because I'm putting it in right there. And then this will be 2 times n plus 1 plus 1. Close that. Ooh, let me write that a little bit better here. There we go. And then on this side, it's all over 6. Okay. So again, what do I notice? 1 squared, 2 squared, 3 squared, plus blah, 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 n squared. This will be the term that comes after it. All of this we are going to substitute. All right, we're going to substitute this guy in right here. All right, so this will turn out to be n times n plus 1, 2n plus 1, all over 6, and then plus n plus 1. I'm going to write this out as n plus 1 twice. Okay. On this side's going to be cleaned up just a little bit. So if I think about this, this will be n plus 1, n plus 2, and this would be 2n plus 2 plus 1. So this would be 2n plus 3 all over 6. So that's a little cleaned up version. Okay. So we have to manipulate it, right? So I'm going to go ahead and multiply things together. So this will be n times 2n squared plus, this should be 3n plus 1, and then all over 6. And over here, this will be n squared plus 2n plus 1, right? Manipulate this a little bit more. So 2n cubed plus 3n squared plus n all over 6. And what I'm going to do on this is I am going to multiply by 6 over 6. So this will become plus 6n squared plus 12n plus 6 all over 6. Okay, I'm going to run out of space, so I'm going to add a new page, but I'm just going to go ahead and collect our like terms. So if I do that, this will become 2n cubed plus 9 squared plus 13n plus 6 all over 6, right? Because 3 plus 6 gives us our 9 squared, 1 plus 12 gives us our 13, and so forth, right? And so now you might have forgotten how to factor our polynomial, so of the third degree. So what you can do is you can actually have scratch paper. So off to the side, I'm going to call this my scratch work, which is not really a part of my proof. Now, I need this polynomial to be these 3 binomials. So what I'm going to do is I'm going to multiply these 3 binomials together and see if it gives me the 2n cubed plus 9n squared plus 13n plus 6, right? So I'm going to rewrite this. So n plus 1 times n plus 2 times 2n plus 3. So let's go ahead and multiply this together. So this will become n squared plus 3n plus 2. And multiply that by 2n plus 3. Again, 1n plus 2n, that gives us our 3n squared. And then let's manipulate this. So n squared, so this will become a 2n cubed plus 3n squared. And then plus 6n squared plus 9n. And then last one, plus 4n plus 6. Collect our like terms. 2n cubed plus 9n squared, looking like this one over here. 9 plus 4 does give me 13n, and then plus 6. So notice that I got the same polynomial as this guy, so I know that this would factor into this. So that means, because again, I'm focusing on my blue writing, that means that this would turn out to be n plus 1 times n plus 2 times 2n plus 3, and then all over 6. Notice the left side was equal to the right side. So since this is equal, we get to say, right, by mathematical induction, right, the above statement is true for all natural numbers. Right? So it'd be true for 1, 2, 10, a million. We just don't have to prove that it's true, because if 2 works, then I already know that 3 is going to work. And if 3 works, then I know 4 is going to work. And if 4 works, 5, and so forth and so on. And that is mathematical induction.